All right, section 5.4 is on sampling distributions and the central limit theorem. The probability distribution of a sample statistic. So when we're talking about the sample distribution, we're talking about the probability distribution of a sample statistic. So this is formed when samples of size n are repeatedly taken from a population. And it is the sampling distribution of sample means. So basically, we're going to repeatedly take sample sizes, different samples of size n from a population. So let's say that's size 10. So I'm going to take a sample of size 10, calculate the mean. Take another sample of size 10, calculate the mean. Take another sample of size 10, calculate the mean. And then what I'm looking at is the distribution of those sample means. So this is different from just I pick one person from a sample, then I pick another person from a sample and another person from a sample, which is what we were looking at before. The sampling distribution of X, where X is taken from a certain population. Okay, so it looks like this. So we start with a population with a certain mean and standard deviation. And then I take my first sample and I take my first sample and I calculate the mean from that one, and I call that X bar sub 1. And then I take a second sample of size n and I calculate the mean of that sample and I call that value X bar 2. And then I take a third sample and I call the value of that mean X bar 3. I take a fourth sample. They all have the same sample size n. So I take another sample of size n and I call the mean of that sample X bar 4. And I just keep doing that. So the sampling distribution can consist of the values of those sample means, X bar 1, X bar 2, X bar 3, and so on. So again, these are, I took a sample and calculated mean. It's not just I grabbed a person out of the population and called it X, okay? So the mean, now I have all these sample means. So this is now my data. And I can take the mean of the sample means. And the mean of the sample means is labeled mu of X bar. And this is going to be equal to the population mean. So my expectation is that if I take a sample, the expected value of this mean, X bar 1, is the sample mean. I expect this one to be the sample mean, and so on. So if I take the mean of all of these, I also expect that to be the sample mean. Okay, so the mean of the sample means is going to be just the mean of the sample. But because I took sample means, the standard deviation is going to be smaller than our standard deviation of our population. So the standard deviation of the sample means, we call that sigma X bar, is equal to the population standard deviation divided by the square root of the sample size. So it's sigma over the square root of n. So this, like I said, this now becomes my data. And if I calculate the mean of all these values, I'll get back the population mean. And if I calculate a standard deviation from these values, I'll get sigma over the square root of n. And this sigma over the square root of n is called the standard error of the mean. Standard error of the mean. Okay, the central limit theorem says that if the samples of size n greater than 30 are drawn from any n greater than or equal to 30. This is why that 30 is so important and why I asked for you to try to have 30 values for your project. If n is greater than or equal to 30, if samples of size n greater than or equal to 30 are drawn from any population with a mean mu and a standard deviation sigma, then the sampling distribution of the sample means will approximate a normal distribution. So even though the population itself might look like this, which is clearly not normal, when I look at all my sample means, if I draw the distribution of those, that distribution will be normal. As long as my n is at least 30, this distribution will be normal. And the greater the sample size, the better that approximation will be. Okay, so that's the first thing. I can take any population, and if n is greater than or equal to 30, the sampling distribution of the sample means will be approximately normal. And the mean of this distribution will be that mu x bar, which is mu, and the standard deviation will be sigma x bar, which is sigma over the square root of n. And then it also says, so it has two parts, that's the first part. And the second part is if the population itself is normally distributed, then the sampling distribution of any sample mean, doesn't matter what the size n is, the sampling distribution of any sample means is normally distributed for any sample size. So again, the sampling distributions of the sample mean, the mean will be mu, and the standard deviation of the distribution of these sample means will be sigma over the square root of n. So I just want to give you a simple case of this. If n was 1, so I took samples from the population of size 1, which means I basically just pulled x values out of my population. Well, it's normal, so that'll also be normal. And the mean would be mu, and the standard deviation would be sigma over 1. It would just be sigma, which makes sense. If I just pull random variables x, it's going to be those are going to be distributed mu, comma, sigma. Okay, but for any other size, the standard deviation is going to become sigma over the square root of n. So in either case, the sampling distribution of the sample means has a mean equal to mu, the population mean, and the sampling, the variance of the sample means is going to be sigma squared over n. The variance is sigma squared over n, which means the standard deviation is sigma over the square root of n. And again, this is called the standard error of the mean. Okay, and here it's showing you how the central limit theorem works. If you take any population and n is greater than or equal to 30, then the distribution of the sample means will be normal, and the mean will be mu, and the standard deviation will be sigma over the square root of n. And if the underlying population is normal with mu and sigma, then the distribution of sample means for any n will be normal, and the mean will be mu, and the standard deviation will be sigma over the square root of n. And so when we want to transform an x bar to a z-score, we're going to use, instead of using just x minus mu over sigma, we would use x bar minus mu of x bar over sigma x bar. So this becomes x bar minus mu, because this is mu, over sigma over the square root of n. So this is how we do our transformation. Right, and that is the end of that section. And I'm going to see if I can copy this slide. Okay, I recommend that you copy this slide and put it into your Excel spreadsheet, because it gives you all of the information from the previous slides is included in this one slide. All right, so we are now ready to do the homework problems from section 5.4. So that's number 10 and 11. So let's go here and look at number 10. So it's showing us a graph. Let me pop this out. Okay, so this graph is the annual snowfall distribution in feet for a particular county is shown with its mean and its standard deviation. So it has a mean of 4.2 and a standard deviation of 2.4. Assume that a sample size of 100 is drawn from the population. So we draw a sample of 100, determine which of the graphs would most closely resemble the sampling distribution of the sample means. Okay, so if we draw a size of 100 from the population, and we draw a bunch of those, by the central limit theorem, since although this is not normal, right, but because this is greater than or equal to 30, it's going to be normal. So let's look here. So my graph is going to be normal, and these all are. And then my mean is going to be 4.2. So these two have a mean of 4.2. This one does not. So my mean is going to be 4.2. And my standard deviation is going to be sigma over the square root of n. And sigma is 2.4. Let me pop this back out. So my mean, it's going to be normal. My mean will be 4.2. And my variance, or sorry, my standard deviation will be sigma over the square root of n. And the square root of n is 10. They made this easy for us. So the standard deviation is going to be 2.4 over 10 or 0.24. So it should be 4.2 and 0.24, which is this one, 4.2 and 0.24. All right. The graph most closely resembles the sampling distribution of the sample means because mu of x bar equals 4.2 and sigma x bar equals 0.24, and the graph approximates a normal curve. About 75% of all female heart transplant patients will survive for at least 3 years. 60 female heart transplant patients are randomly selected. What is the probability that the sample proportion surviving for at least 3 years will be less than 72%? Assume the sampling distribution of the sample proportions is a normal distribution. The sample mean of the sample proportion is equal to the population proportion, and the standard deviation is equal to the square root of PQ over N. So it's telling me that the sampling distribution of the sample proportions is normal. Okay, so 75% of all heart transplant patients will survive for at least 3 years. Let's put this in Excel just to keep track of it, if nothing else. Right, so this is number 11. Okay, so 75% of, about 75% of all heart transplant patients will survive for at least 3 years. So let me just put that in here. 75% survive. Okay, and then it says 60 patients are randomly selected. So N is going to be 60. What is the probability that the sample proportion surviving at least 3 years will be less than 72%? So they want to know what is the probability that the number surviving at least 3 years is less than 0.72. So that's what they want to know. 75% on average survive at least 3 years, and they want to know what is the probability that the number surviving at least 3 years is less than 72. So this is what they're looking for. Okay, and then it gives us some more information. Assume the sampling distribution is normal and the mean of the sample proportion is equal to the population proportion. So what that tells me is that the mean is going to be the mean of the sample proportion is equal to the population proportion, and they gave us that. The population proportion was 0.75. So the mean of the sample proportion is also 0.75. Okay, and that the standard deviation is square root of PQ over N. And for sigma equals the square root of PQ divided by N. Okay, so I need to find my sigma. So this is my P. Okay, so P is 0.75. Remember, Q is 1 minus P. Okay, and then my N was up here, 60. I'm just going to go ahead and put it down here again. Right, so my sigma is going to be the square root of P times Q divided by N. Is that right? My sigma is P times Q divided by N, the square root of that, root of PQ over N. Okay. And again, I recommend you put in my numbers and make sure. So here's our mean. Here's our standard deviation. All right. And then we want to know that the probability that the number surviving at least 3 years is less than 0.72. So basically, this is my X. Okay. So I have my mean, I have my sigma, and then I have my X. Okay, and I want the area. This is going to be, because of this, I want the area to the left of X, where X is 0.72. Okay, so this less than, so this is the area to the left. So now I can just use my regular normal distribution to find that probability. Okay, so I'm going to go probability that X is less than 0.72. That's going to be norm dot dist. This is the one that gives me back a probability. Okay, and remember we put in here X, mean, standard deviation, cumulative. So X, comma, mean, comma, standard deviation, comma, true. And I got 0.295. Again, this is norm dot dist, X, comma, mean, comma, standard deviation, comma, true. And I got 0.29. How many decimal places do they want it to? 4. 0.2958. Okay, and that's the end of 5.4, and then we can do section 5.5.